Hello, AP Chem. Hope you are doing well. Today's goal is to work about really the difference between delta G and delta G naught. So we really want to understand those concepts. They're really important concepts. They tend to be a little bit difficult to get. In the end, the calculations will not be too bad because you're just going to be plugging into some formulas. But it's important that you understand the concepts as well. So we're going to spend some time doing that. So here we go. So Gibbs free energy, obviously, that's delta G. And so this is delta G without the naught. So delta G is the maximum amount of useful work that can be done by the system. So if it's a spontaneous process. So all spontaneous processes, you get useful work from them. So to understand what delta G is, first we're going to look at what you did in physics, where you defined work as the force exerted over a distance. So work is force times distance. So in this model over here, this actually came from a Pogel. You have a ball at A and you have a ball at B. So, and the ball is rolling down the hill towards C, right? So the ball is moving this way. So the question here is more work done when the ball falls from A or when it falls from B? Think of that for a second. Hopefully you said A, right? Obviously, it has further to fall when it goes from A, and it has less far to fall, and so the distance is shorter, and so you can do less work when you fall a shorter distance. How about number two? Is more work done when the ball falls from A or from E? So here now we're comparing A or from E. So E, you're going to roll this way as well. Hopefully you said that the same amount of work will be done. And it's because why? It's traveling the same distance, right? It's leaving from the same height, right? Same distance. And so the same amount of work is going to be done. So that's our concept. So now we want to make the analogy with a real chemical reaction and how you can get work done by a chemical reaction. So here we have another model here. Model 3 is this graph of delta G versus Q P in this case. So it's just like Kp, but it's a Q. And it's pressures. It's in pressures because it's for this reaction here where we have all gases, and so the Kp is given to us. And so they plotted the delta G as this reaction proceeds versus the reaction quotient. So as you move this way to the right, the quotient is increasing, and so what that means is Q is always products over reactants, right? And so as Q gets bigger, you get more and more products. So in a sense, you're doing the reaction in that forward direction as Q gets larger. Okay, so we're kind of, as we go across, the reaction is proceeding. So it says put an X on the graph to indicate where the reaction is at equilibrium. So hopefully you realize the K is 6 times 10 to the 5th. And so we're going to find that that's this part right here, right? Everything's times 10 to the 5th. And we're just going to read up, and I'm just going to put an X there. So that is where Q is equal to K. And you'll also see that that is also where the delta G is equal to 0, right? So we're at the K, and also the delta G is equal to 0. So that means we are at equilibrium, right? So this spot here, we are at equilibrium. It is where we have delta G is equal to 0, which that means it's at equilibrium, and also Q is equal to K. So we're at the K, we're at the equilibrium constant, and so we must be at equilibrium. Okay, so that's question number 3. Number 4, put in arrows to show the spontaneous direction starting from Q equals 3 times 10 to the 5th, and then you're going to Q equal to 10 times 10 to the 5th. So from 3 to 10. So here is 3. So I'm going to put a dot there, and then we're moving along until we get to 10, which is right there. Okay, so obviously we're proceeding like in this direction, right? In that direction. Okay, so I'm sorry. So when we start at 3, Q is equal to 3, we are going to be moving, you would be moving in this forward direction because you want to get to K, which is right here. So obviously here, when you're at Q equals 3, one thing to think about is when you're at this point, the Q is less than the K, right? Because your Q is 3 and the K is 6, right? So Q is less than K, so what does that mean? You have fewer reactants. I'm sorry, you have fewer products than you need at equilibrium. So you're going to have to proceed in this right-hand direction to get more and more products and to end up at equilibrium. So you would proceed in this forward direction. So that's going to be the spontaneous direction, right? Spontaneous direction is moving in this forward direction. And now if you're coming from 10, you're starting here. Well, which way is the reaction going to go? The reaction is going to proceed to go to equilibrium. So you're going to proceed in this direction is the direction the reaction is going to proceed so it can get to equilibrium. So at this point here, the Q is at 10, equilibrium is at 6. So Q is greater than the K. So you have too many products. And so the reaction is going to proceed towards reactants, and you're going to go in the left-hand direction, which is, so it would be spontaneous in that left-hand direction, right? And it would go to the left. So you always want to get to equilibrium. Can more work done by the reaction? Can more work be done by the reaction if Q equals 3 times 10 to the third or Q equals 5 times 10 to the fifth? I think I meant 3 times 10 to the fifth here. So let's fix that. So when is more work done by the reaction? If we start here at 3, we're going to move this direction to get to K. If we start at 5 times 10 to the fifth, we would be starting here, and it would move in this direction to get to K. So take 2 seconds. Which one would have more work being done? Correct. You want Q is equal to 3 times 10 to the fifth. Why? Because you're further from K, right? It's just like the ball is further, it's going to fall further. This reaction is going to proceed further to get to equilibrium. It's farther away from equilibrium, so it can proceed further to get to equilibrium. So reaction is further from equilibrium is one way to think of it. It's going to proceed farther in order to get to equilibrium, okay? So the further away you are from equilibrium, the more work that can be done. That's the point there. Number 6, if a system goes from 7 to 9, is work being done by the system or work being done on the system? All right, so we're going from 7 to 9. So 7 is here, and then 9 is here. So we are moving from 7 to 9. So is that the spontaneous direction or the non-spontaneous direction? Hopefully you said that's the non-spontaneous direction, because remember, spontaneous direction is going to be going to equilibrium, which is right here. So we're moving in the opposite direction. So this is the non-spontaneous direction when you're moving to the right, away from equilibrium. So if you're going in the non-spontaneous direction, the system must be doing work, right? So the system is doing work on the system. Okay, let me say that one more time. I think that was confusing. Okay, so we're moving in the non-spontaneous direction. If it goes in the spontaneous direction, the reaction would be doing work. So in this case, you're going in the non-spontaneous direction. Work would have to be done on the system, right? Work done on the system. It's like you have to put in work to get that non-spontaneous direction to occur. Work done on the system because move in non-spontaneous direction. Okay, so hopefully all of that makes sense. Let's see if we can summarize it here a little bit. I know it can get a little bit tricky. So we had this scenario here when we were out here and Q was greater than K, and we had Q is less than K. So when Q was less than K, the reaction proceeded spontaneously in the forward direction to get to equilibrium, right? So you needed more product, so you move in the forward direction to get to equilibrium. When the Q was greater than K, that was the situation here where you needed to go back to the left to get to equilibrium. You had too many products and you proceed to the left to get to equilibrium. So when Q is greater than K, you're going to proceed in the reverse direction. So that's going to be when you have a positive delta G. So notice up here, I didn't point this out earlier, when we had Q is less than K, when you read across, you see that your delta G was negative, right? And you were proceeding in the forward direction, was spontaneous. When you have up here, where you have a positive delta G, you are going to move in the reverse direction, is the spontaneous direction. So that means the forward direction is the positive delta G. So it's non-spontaneous in the forward direction, so it's spontaneous in the reverse, okay? When there's a larger difference between Q and K, like you're further from equilibrium, right? More work can be done by the system when it goes towards equilibrium. So, just when you're further away, you can do more work. All right, that's kind of the concept of what delta G is. Now let's look at a couple more little things that work. So there's a relationship between Q, K, and delta G, and it really comes all together in this formula here. And it kind of puts together all the concepts that we really have already just come up with. So let's see if we can see how this equation kind of fits the concepts we just came up with. So a reaction is spontaneous in the forward direction when you have Q is less than K, right? You have too few products. You need to move in the spontaneous direction, in the forward direction, in order to get more products. So that's going to happen when Q is less than K, Q over K is less than 1, right? So you have like a decimal, right? A decimal here. And so you're going to have a negative exponent, right? When you have Q over K is less than 1. So when you take the ln of Q over K in this situation, when you take the ln of a decimal, you're going to get a negative value because the exponent is negative. And so because of that, when you plug in and get your ln of Q, if that comes out negative, you're going to end up with a negative delta G. So when we see that we have a negative delta G, we know that Q is less than K, and we would be spontaneous in that forward direction. When the reaction in equilibrium, it's very easy. Q is equal to K, so obviously Q over K equals 1. You take the ln of Q over K, which is equal to 1. Ln of 1 is equal to 0, right? So e to the 0th power is equal to 1. So delta G is equal to 0. So when delta G is equal to 0, you are also at equilibrium. And then obviously the opposite, Q is greater than K. That's going to be greater than 1. That's going to be a number with a positive exponent. And so the ln of it is a positive value, which means that our delta G is positive. So we want to start thinking about, when a reaction is non-spontaneous in the forward direction, that's when you have that positive delta G. When it's spontaneous in the forward direction, you have a negative delta G. So the delta G tells you whether you're spontaneous or not in the forward direction, and it obviously has to do with the Q and the K and whether you have too few products or too many products. And it's all kind of summarized in this formula here. And so it's relating Q, K, and delta G. Hopefully that makes sense. All right, so now what we want to do is we want to talk about this delta G naught, which we haven't talked about yet. It's always a little confusing between delta G and delta G naught. So just make sure we try to get that difference. So let me point it out to you. So delta G we've already done is RT ln of Q over K. Now we can modify this and rearrange it, and you can rewrite it. Delta G is RT ln Q minus RT ln K, just using our rules with ln, right? Okay, so now we have this new equation. So now what we're going to do is we're going to imagine that the system is at standard conditions, and it's very important that you know what those standard conditions are. Standard conditions is 1 atmosphere if you're doing anything with gases and you're doing pressures, or if you're doing solutions and you have concentrations like KCs, then all your concentrations are 1 molar. So what that means is that your Qs are always going to have a value of 1 when you're at standard conditions, because you either have all values of 1 for your pressures or you have all values of 1 for your concentration. So the Q is always equal to 1 when you're at standard conditions. So what that means is now we can plug into this equation here and just plug in a value of 1 for the Q, okay? So if you plug in a value of 1 for Q, because you're at standard conditions, what we're going to do is we're going to change the delta G to delta G naught. That naught tells us that this is the delta G at standard conditions. So delta G naught at standard conditions, that Q is going to be equal to 1. And so when you solve this now, the ln of 1 is equal to 0, right? So this whole term is going to go to 0. And so what that means is the delta G naught is equal to negative RT ln of K. And that's our new equation here. We're going to use this equation all the time to be able to go between K and delta G naught. So the confusion is that delta G naught is really telling you whether the reaction is spontaneous or non-spontaneous when you're starting at standard conditions. When you're at standard conditions, the delta G naught tells you whether you're spontaneous or not, whether it's positive or negative. If it's a negative delta G naught, it's spontaneous at standard conditions. And if it's a delta G naught that's positive, it's non-spontaneous if you start at standard conditions. But the thing is that it's also related to K, right? And it's kind of for those same reasons. So if you have products are favored over reactants at equilibrium, we know K is greater than 1, right? You end up with more products compared to reactants at equilibrium, your K is greater than 1. If you take the ln of K, that's going to give you a positive number, which if you plug that back into this equation, obviously gives us a negative delta G naught. So the interesting thing is, if anytime you have a negative delta G naught, it's telling you that at equilibrium, you are going to be favoring products over reactants at equilibrium, okay? If your delta G naught is positive, it's also telling you that the K is less than 1 because you get, fewer you have fewer products compared to reactants, right? So reactants are favored over products, right? So now there's this, so if you know that the delta G naught is positive, your K is less than 1. You're going to have reactants being favored at equilibrium, right? So the delta G naught being positive tells you it's not spontaneous when you're at standard conditions, but it also tells you at equilibrium, the reactants are more favored. You have more reactants compared to products. So that's really, really powerful that it kind of tells you both of those things. All right, so this chart is really, really important. And on the next page, we have some graphs that are really going to give us these same concepts, but in kind of a graphical way to represent it. So these graphs could be a little bit confusing to understand, but I think it will help you in the end to get all of these concepts. So let me try to work you through this. So this graph, first of all, let's look over here on the left. We have a reaction, A going to B. And in this particular case, they're telling you that K has B over A greater than 1. So we're starting, so it's like you're doing the reaction from left to right. You're starting here on the left with pure A. So you're starting all of A, so you have all reactants. And then as the reaction goes to the right, you keep reacting, and eventually you're going to get all of B, right? So you go from all pure reactants to pure products. So that's like the whole course of the reaction. So obviously in this case, you end up at equilibrium right here, which is where your delta G is equal to 0. Okay, that's your lowest delta G. So this is equilibrium right here. So when you have, this is always so confusing. So, okay, so basically as you go and you proceed, you're going to get to equilibrium. When you have the lowest amount of free energy, that's at equilibrium. That's, you know, your most stable spot there. Okay, so what I want to get across here is if you start here, right, and you have some delta G, and you have pure A, right? The reaction's going to keep going to the right until it gets to equilibrium, correct? So along this whole time, the delta G is less than 0, which means it's negative, and so it's spontaneous in this forward direction, right? And the reason must be that Q is less than K, right? So you have fewer products than you need at equilibrium. Because remember, here is when you're at equilibrium, when Q is equal to K. So the reaction keeps proceeding to the right, getting more and more products until the Q gets up to the K and you're at equilibrium. Okay? Now, if you kept going, right, it's going to be non-spontaneous if you keep going past equilibrium, because now you have too many products and you have more than what you need at equilibrium, right? So it would go back to the left to get to equilibrium. So that's kind of the idea there. So moving in this direction, you have a negative delta G, right? You're spontaneous. Anywhere along here, you're going to move in the forward direction to get to equilibrium. If you're moving in this direction, if you start here and you move this way, you're going to be non-spontaneous in the forward direction. You have a positive delta G, right? So it would be spontaneous going to the left. So you have a positive delta G moving in the other direction there. If you started here and you're trying to go that way, it would be non-spontaneous. Okay, so if your delta G naught, okay, now what is the delta G naught? Remember, delta G naught is when you're at standard conditions. And the thing about standard conditions is everything has the same concentration of 1. So if you start with pure A and you keep going, basically at this 50% of the way, you have changed so that you would have the same concentration of A and B. So that would be like they're all 1 molar. They all have the same concentration. That's when you're at standard conditions. So if we read here, this would be when you are at the delta G naught, okay? And so it's kind of that would be, you know, whether you're spontaneous. Your delta G here is telling you whether you're spontaneous at those conditions. So obviously in this case, we have a negative delta G naught because at standard conditions, we're going to be spontaneous in that forward direction. So at this point here, your delta G naught, well, your delta G, which is also your delta G naught because you're at standard conditions, is going to be spontaneous in that forward direction. okay? So basically it tells you if you have a negative delta G naught, it's going to tell you that at equilibrium, you're going to end up with more products compared with reactants because your equilibrium is further to the right of where you would be at standard conditions when you have the same concentrations, one of everything, okay? So that's your negative delta G naught. And so it ends up like this is going down, which is giving you that delta G naught is less than 0, it's negative, and your K equilibrium at this point here, you have more products compared to reactants, right? That ratio you have is greater than 1, right? So K is greater than 1. Okay, so the difference over here is really the opposite, obviously, right? So again, now you're starting with all of C going to all of D, just so we have a different reaction. But again, at this point here is where you're at standard conditions, and that would be your delta G naught. And at those standard conditions, in this case, the spontaneous direction would be to move in this direction, would be the spontaneous direction, right? So now your delta G naught here is a positive value. It's non-spontaneous in the forward direction, right? So you're going to be non-spontaneous in the forward direction, so you're going to have your positive delta G naught right here. And it tells you that you're non-spontaneous in the forward direction when you're at standard conditions. And it's because you're going to be spontaneous in the reverse direction so that you can get to equilibrium. And notice at equilibrium, you're going to have a lot more reactants because you haven't reacted much of your reactants and a lot fewer products, right? So at equilibrium, you have Q equals equal to K, right? But your K, is going to be a lot less than 1, right? Your K is less than 1. K is less than 1. Here, our K, where should I write it? K is greater than 1, right? You have more products than reactants at equilibrium. Here you have more reactants than products at equilibrium. And so it works out that, you know, when your equilibrium is way here on the left, your standard conditions is more to the right. Okay, so you would proceed in the left-hand direction to get to equilibrium. When your K is way over here towards products, you're going to be spontaneous when you start at standard conditions, and so you have a negative delta G naught in the forward direction. Okay, so hopefully that kind of tells you how the delta G naught kind of relates to your K, whether it's less than 1 or if it's greater than 1, favoring reactants or favoring products. So that's kind of the key. So K being greater than 1 is a negative delta G naught, and you end up with more products than reactants. Okay. So those are all the concepts. That's the hard part. All right, so now let's see if we can just do some calculations. I'm sure you're going to have some questions on what we just went over there. You might have to stare at it a little bit until it makes sense to you. All right, so now we are going to get the relationship between delta G and Q. So I'm not taking, not delta G naught, but delta G related to Q. Okay, so what we need to do, we need to start with our same equation that we had on the front. We had delta G was equal to RT ln Q minus RT ln K. We're going to start with that, but now we also know that delta G naught is equal to negative RT ln K. So we're going to take this part here and we're going to substitute delta G naught into our equation right there. And obviously that negative RT ln K becomes our delta G naught, and we still have left the RT ln Q, which is right there. I just changed the order of them, but that's the same thing, okay? So now we have a new equation. We're going to be giving this to you. It's not on your reference chart, but we'll give it to you if we ever have a test. And it's useful because obviously now we have our delta G naught, we're going to have Q, and we can solve for delta G of the reaction, which remember is going to tell you whether the reaction is spontaneous or not, starting at whatever conditions you have of Q, right? So we don't have to be at standard conditions. All right, so here we have a reaction. I'm giving you the delta G naught. So again, remember, that's telling you that it's spontaneous at standard conditions. So we're not going to be at standard conditions, and we're going to try to get the delta G when we're not at standard conditions. So first, a good idea is to write the Q expression for the reaction. So remember, Q is just like K, except so we're not at equilibrium. So products over reactants. In this reaction here, products, we have the NH3. Oh, let's do, these are all gases. So we're going to do the KP, or the QP, right? So in pressures. So I'm going to write it as the pressure of NH3, and we're going to square that. And then we're going to do products over reactants. So we have what? The pressure of the N2. And then we have the pressure of H2. Don't forget you need to cube that. So that is our expression for the Q. Okay, so now what is Q equal to at standard conditions? Now remember, we're doing this with pressures. So if you remember, standard conditions and pressures, everything has a value of 1 atmosphere. So I'm just going to plug in that Q at standard conditions, right? We would plug in 1 atmosphere over 1 atmosphere times 1 atmosphere, and you would cube it. Obviously then, at standard conditions, the Q is equal to 1. Q is always equal to 1 when you're at standard conditions, right? Is the reaction spontaneous at standard conditions? What are we going to look at for there? Yes, hopefully you remember delta G naught. That is telling you whether it's spontaneous at standard conditions by looking at that sign. So it's negative. That should tell you that yes, the reaction is spontaneous at standard conditions because you have a negative delta G naught, right? So negative delta G naught. And remember, well, right, so this is the delta G at standard conditions is negative. So yes, it is spontaneous at standard conditions. Okay, because it's the same as the delta G in this case, right? Because we're at standard conditions, that's the delta G. It's going to tell you that you are spontaneous because you are negative 33.32 kilojoules. Okay. All right, so now I know this is taking a while, so if you need to take a break, take a break. What is the equilibrium constant Kp for this reaction? All right, so now we're going to use, we have the delta G naught, we can use that to get the Kp, and we're just going to use this new equation here. So the delta G naught is equal to negative RT ln of K. We're looking for the K. That's going to be our Kp. All right, so we got to rearrange this a little bit. So what I'm going to do is I'm just going to move the RT over here. So delta G naught divided by RT, I'm going to move the negative over, is going to equal to ln of K. All right, so now let's do K is e to the negative delta G naught over RT, right? So just use your log there, K is e to the negative. Okay, so now let's just plug in some numbers here. K is equal to E. Negative delta G naught is our negative 33.32. And I'm going to get rid of my units. Everything needs to be in kilojoules though, so it's all consistent. Those are kilojoules there. We're going to divide by RT. Now, R is the gas law constant, but we need the one that's in kilojoules, not the one with the atmospheres, not the 0.0821. So we need to use the 8.31 that's in joules per Kelvin. I'm going to change that 8.31 to be in kilojoules, so 0.00831 for is in kilojoules per mole. So this is in kilojoules as well. Okay, so we need to be consistent. So that's R. We need to multiply by temperature. Temperature obviously has to be in Kelvin, so 298 K. Okay, so if you calculate all that, it should be E to the 13.455, and that should give you a K that is equal to 6.97 times 10 to the 5th. Okay, so there we go. Now, one thing to know, that K is much greater than 1, right? So K is greater than 1. We should know that then that should mean that our products are more favored at equilibrium than reactants, right? So this next question here, by comparing Q and Kp, one can also determine that the reaction at standard conditions is. So if you were at standard conditions, would this reaction be spontaneous? How should we figure that out? Well, we know that Q at standard conditions is a value of 1. At equilibrium, our value is much greater than 1, right? So at standard, Q is equal to 1. At equilibrium, it's 6.97 times 10 to the 5th, right? So Q is much less than the K, right? Q1 is much less than Q1 is much less than the K. So we have too few products, right? The Q is less than the K. We have too few products. It needs to proceed in the forward direction, spontaneous in the forward direction. It will go in the forward direction to get to equilibrium, so it gets more products, right? So the Q is less than the Kp. You are going to need to proceed in the forward direction, which means it's going to be spontaneous in the forward direction and when we're at standard conditions, right? So this situation, I just want you to realize, is the situation when our K is greater than 1 and our delta G naught is negative. And so remember, that's the situation in this graph here. So our K is a relatively large number. We have a negative delta G naught, and we're going to proceed in the forward direction. If we start it at standard conditions, we're going to proceed in the forward direction to get to equilibrium. So we have a negative delta G naught, and we have a K that's greater than 1. Okay, now so that was when it was at standard conditions. Now we're going to change the conditions. Instead of being at standard, we're going to increase the pressure to 3 atmospheres for just the hydrogen gas. So now we're at a new Q. We're not at equilibrium, but we're not at standard conditions either. And we want to know, is the reaction now more or less spontaneous than it was at standard conditions? So what you want to think about is like, okay, when you were at standard conditions, your hydrogen was 1 atmosphere. So let's think about our reaction just Le Chatelier. We had at standard, you had 1 atmosphere, 1 atmosphere, and 1 atmosphere. Now we're increasing the amount of hydrogen to 3 atmospheres. So we have more reactants than we did at standard. You've got too many reactants. What is it going to do? It's going to proceed to the right to get to equilibrium. You've got too many reactants, too few products, right? So that's what we can explain. So we increased H2, which is a reactant, right? So we have too many reactants, too few products, which is reactants. So we have more reactants now than when at standard conditions. Okay, So from this Q, the reaction's going to proceed in the forward direction, right? To get to equilibrium. We've got too many reactants, it's going to go to the right. So remember, even at standard conditions, we were going to the right, right? So now we're like even further away, and we're going to go even more to the right. It's like we're starting with even more reactants. So the situation was this graph here. When we were at standard conditions, we started here and we went to equilibrium. Now we're starting maybe here and we're going to equilibrium. So we just have further to go to get to equilibrium. So it should be more spontaneous. We should be able to do more work to get more work when we go towards equilibrium. All right, so the reaction proceeds in forward direction to get to equilibrium. Too many reactants, right? Because our Q is products over reactants. We just added more reactants, right? So Q is now even less than the Q at standard. And that Q at standard was even less than the K, right? So we have to get all the way to the K. So you're further from K. Further from K than at standard conditions. Okay. So we should be able to do more work. So let's see if we can do more work. We're going to calculate the delta G and see if we can do more work from this position, and we should. So delta G is equal to delta G naught. So we're using this equation here. We're using this one here. Delta G is delta G naught plus RT ln Q. So we're going to plug into that equation there. Okay, delta G naught is our negative 33.32 kilojoules plus RT, so 0.00834. Again, make sure you have kilojoules per Kelvin. There's per mole in there too. I'm just not writing that in. And the temperature is 298. All of this has been at 25 degrees Celsius, I think we said in the beginning of the question. And then ln of Q. Now, what is Q in this case? Q, I'll write out what Q is, right? Q is products over reactants. We were all at standard conditions except we changed hydrogen to be 3 atmospheres. So when we plug in our Q, you know what? I'm going to do Q over here on the side. Q is going to be products, which was the NH3, and we're going to square that, over the N2, which is 1 atmosphere, and the H2 now we have changed it to 3 atmospheres, and we have to cube that. So that's the value of Q. It's like 1/27th, okay? If you divide 1 divided by 27, you will get the value of 3.7 times 10 to the minus 2. So no longer is our Q equal to 1. We now are not at standard conditions, and that's what it happens to be. So the Q is plugged into there. Okay. Whew. So now delta G, if you calculate all this out, this whole thing is going to equal, comes out negative 8.16 kilojoules. And if you calculate that, our delta G is equal to negative 41.5 kilojoules. If you want to put kilojoules per mole, that's fine. It's officially kilojoules per mole of reaction, okay? And that would be our answer there. Now, I want you to compare this delta G from the delta G naught. Our delta G naught was negative 33.32, right? This negative 41 is even more spontaneous, we say. So what it is it's further away from equilibrium, right? So kind of you can think of it as more spontaneous than at standard conditions. So what that means is more spontaneous, you're further from equilibrium. More work can be done by the reaction, right? So you're further from that equilibrium position. And that makes sense because we had more reactants, so we were further from equilibrium. All right, that was the hard part, to really understand those concepts there. I've got one more calculation to do. So let's move to that. And then we have a little bit easy part on the last page. Okay. All right, let's move to our last example here. Just wanted to do one more calculation so you understood kind of what situations we run into. All right, so I'm giving you another reaction. This happens to be ammonia in water, which is obviously a base in water, which means it's the reaction that we can write the K as the Kb, right? It's the equilibrium constant for a base in water. So the K now just happens to be the Kb, but it's just a K, just like any other K. So the K can be a Ka, a Kp, a Ksp, Kb, whatever K it needs to be. A Kc, it could be any K. All right, so this question, what direction will the reaction go given these conditions? So I'm giving you these conditions. It's not standard, right? And we're going to try to eventually solve for the delta G. So first we need to find Q because we're not at standard conditions. Q is products over reactants, just like we've always had. In this case now, we're just going to plug in those conditions. We're finding the Q. The NH4 plus is our 0.10 molar. OH minus is 0.050 molar over the NH3, 0.10 molar. Okay, calculate that out. 0.050, and the K is 1.8 times 10 to the minus 5. So this is obviously 5.0 times 10 to the minus 2. That Q is a greater number than the Kb, right? So Q is greater than the Kb, right? This is 5.0 times 10 to the minus 2. This is 1.8 times 10 to the minus 5. Okay, so the Q is greater than the Kb. So what does that tell us? It tells us the Q is greater than the Kb. That means we have too many products. Have too many products. So the reaction would proceed in the reverse direction, right? To get rid of products. Proceeds, can't write. Proceeds in reverse direction to get to equilibrium. Okay? All right. So we already can tell that from the Q being greater than the Kb, but let's actually calculate, right? You could just do that and you know it's going to go in the reverse direction. But we could also calculate for delta G, and that would tell us whether we're spontaneous or not in the forward direction. So to find delta G, we're going to need to get our delta G naught first. Since we know the Kb, we can use this equation and solve for delta G naught. So in this case, we have negative, I'm just going to plug it in here. Delta G naught is going to be negative. Again, I'm going to use the 0.008314 kilojoules per joule. Again, there's per mole there too. The temperature, we're at 298. Again, we didn't say, but if they don't say what temperature, just assume 298. ln of K, which is our 1.8 times 10 to the minus 5. So if you calculate all of that out, the delta G naught should give you a value of 27.07 kilojoules. Okay, so that's our delta G naught. Okay, so if you know the K, you can always find the delta G naught. And remember, they're related to each other. When the K in this case is less than 1, it means, you know, you're favoring kind of your reactants at equilibrium, which means you have your non-spontaneous at standard conditions, right? The delta G naught is positive delta G naught, because you're favoring, you've got more reactants at equilibrium. But let's look at our delta G. So we're going to solve for delta G. The delta G naught is positive 27.07 kilojoules plus our 0.008314 times our 298K. And then we need to plug in our ln of Q. Now, what's our Q in this case? We solved for Q up here. This was our Q, right? So 0.050. Okay, so now our delta G should be our 27.07. If you calculate all of this, I have plus a negative 7.42. So I got a total value of 19.65 kilojoules. Okay, so notice the delta G is positive, right? So it definitely tells you it's non-spontaneous in the forward direction at these conditions that we're at, right? With being at this Q that was given to us, it's non-spontaneous in the forward direction. So again, it's telling you it would proceed in reverse to get to equilibrium, right? Non-spontaneous in the forward direction because you have positive delta G, and so it proceeds in the reverse direction to get to equilibrium. Okay, that makes sense, right? And at equilibrium, it should have a lot more reactants compared to products because your KV is a lot less than 1. So it all kind of goes together. Okay. All right, that was the hard part. Here at the end, we just wanted to put in a little bit more about delta G and how if you have a reaction that maybe is non-spontaneous at the conditions you have, there are ways of getting that reaction to happen, and that is by coupling it with a spontaneous reaction at those conditions. So you basically kind of doing both reactions together, and the total delta G then might be spontaneous. So here I have some reactions, and we're going to use delta G naughts because we're going to assume that we're at standard conditions, and we're just going to look at the delta G, you know, if everything was at standard conditions. So in this example, we have a non-spontaneous reaction at these standard conditions where you have a positive 86.2, so it's non-spontaneous, but you could couple it with a spontaneous reaction, right? Delta G naught that has negative 300.4. And so if you did, and you just add up those two equations, you get this total equation, and you can add up your delta G's, and you obviously get a delta G naught, which the delta G then is going to be spontaneous at those conditions, right? At standard conditions. Oops. Conditions, right? So by doing those two reactions together, it can be spontaneous overall. So that's really, really useful, is how you can kind of get non-spontaneous reactions to occur. You have to couple them with a spontaneous reaction. So this happens all the time in our bodies and biological systems, right? So all organisms take in food, such as glucose, and metabolize it in a series of reactions that are spontaneous. These spontaneous reactions are coupled with the non-spontaneous production of ATP. So we take in food, and by coupling it with the production of ATP, which is not spontaneous, you can make lots of ATP. So this is kind of trying to show you how you take in food, but you also make ATP, and so you can get, and then you can couple that with making other other molecules that are more complex, which also would be non-spontaneous. So here it's showing you if you're metabolizing glucose, you burn the glucose with oxygen, get CO2 and water, obviously that's going to be really spontaneous. You're burning sugar, right? Really spontaneous reaction. But the synthesis of ATP turns out to be a non-spontaneous reaction, positive 31. So you can actually do many reactions, make many things of ATP for one, say you had 1 mole of glucose, you could make more than 1 mole of ATP. It turns out you can do about 36 moles of ATP, and I think you're making some other molecules as well, because if you multiply this by 36, you're still going to get less than that negative 2880. So, theoretically, you could couple it with a non-spontaneous reaction that would exactly balance out or leave a little bit to make it spontaneous overall, okay? So this happens all the time. So you can burn glucose to make ATP, and then you can make a dipeptide, right? And that's a non-spontaneous reaction, right? But you want to make some proteins. So how are you going to make your proteins? You need to couple it with the hydrolysis of ATP, which is the breaking down of ATP. So ATP reacts with water and you get ADP. And that turns out to be a spontaneous reaction there. And so if you do both of these reactions, one of each of them, you get a net spontaneous reaction. So that's how, again, you're coupling now the non-spontaneous with the spontaneous reaction. That's why it's so important to burn your glucose to make your ATP, because then you can make your protein by reacting that ATP. So that's your coupling of reactions. There is one additional thought, just again, that concept of like, why do we get so much energy when we break ATP down? And the real reason, remember, it's not that you get energy from breaking a bond. That's not true. It's ATP actually has a -4 charge in the body. And when it reacts with water, you actually break off one of those phosphate groups. This is ATP over here, right? You've actually got 3 phosphate groups, 1, 2, 3 phosphate groups. So that's the triphosphate. And then the ADP has only the 2 phosphates. So you're breaking off one of those phosphates, and it turns out that phosphates have that negative charge. And so does it make sense if you go from a -4 to a -3, there's less electron repulsion, and so the ADP is going to be more stable. So that's what it's telling you here. When you go from the triphosphate to the diphosphate, the ATP is less stable or the ADP is more stable. So that's a reason why it's favorable to break the ATP apart. The other thing is that you also get this HPO42-, which happens to have a lot of resonance stabilization. They're showing you the hydrogen phosphates, and you can see there's a lot of resonance in those structures, and so that's actually a relatively stable substance there. I know that was a lot. Thanks for hanging in there, and good luck with your homework. The homework really shouldn't be too bad as long as you use those formulas that we have. All right, so just make sure you go back. You can go between delta G naught and K. You can get delta G with the delta G naught and Q. Again, just be really careful between delta G is telling you whether the reaction is spontaneous at the conditions you're at, And delta G naught is telling you whether it's spontaneous at standard conditions. But delta G naught also tells you about equilibrium and whether at equilibrium you're favoring reactants or products. So hopefully this all made sense. Good luck with the homework.